Okay, well, good afternoon, ladies and gentlemen. First of all, I would like to thank you for giving me the opportunity to talk and to participate in this conference and present to you my work, long years work. I also wish to tell that I'm happy to be here and to see a lot of familiar faces from the last conference in Japan, Sendai, so it was fun. So my name is Slobodan Stankovic. I'm from Switzerland, near Lake Leman, or Geneva Lake. I'm an experimentalist for almost 15 years, working with oxyhydrogen gas and his possible connection with the LNR. So in this picture here, well, I will tell you later what's it. So numerous experiments produced by George Oshawa, John Barclays, Robert Monti, or Emmanuel Ransford have been conducted with electrical discharge between two carbon rods in deionized water, and some transmutation element was found, such as iron, chrome, cobalt, zinc, were subsequently found in the residues. I've been working with oxyhydrogen gas for almost a decade, and did a lot of experiments with materials such as tungsten, aluminum oxide, graphite. So in this case, I will present you some strange things, and even nuclear transmutation with the graphite and the oxyhydrogen gas. In this setup, you can see elements for the experiment. The graphite rod was 5 millimeter diameter, was placed in the sample feeder. Here, small picture, not see it very well, but you have a graphite here, a graphite rod, and it's pushed under the nozzle of the oxyhydrogen plasma. It is very accurate. You can, it has a resolution of 0.5 millimeter per step, so we can do the precise positioning. And the plasma was generated with the oxyhydrogen electrolyzer, and it's a big electrolyzer. It can produce 1,200 liters per hour. Or 20 liters per minute. To measure all these, in this experiment, we have different setup, different devices, such as small ocean optics spectrometer. We have also high resolution spectrometer built by myself. We have also 360-degree radiation detector. And they're all placed, and he's placed around the contact point here between graphite rod and oxyhydrogen plasma. We can see also in the setup another device is built by myself. It's a 2D axis microscope. But I didn't use it. I didn't use it yet in the experiment. It was for the further experiments. So all these processes control from the control room, the monitoring center. Here. The two-axis. So I said the two-axis microscope radiation detector, high-resolution spectrometer were designed by myself, and that's why it took me a little bit time to put all these experiments in place. So, by the way, thank you, eBay. So this is the complete setup with all the elements here for the where is the gas. Input gas, output gas, input rod, the spectrometer, monitoring center. let's do the experiment. The power used for the electrolysis was 26 volt DC with 60 to 70 amps. So the amount of the oxyhydrogen gas was about 600 liters per hour. The produced plasma was analyzed with the low resolution optical spectrometer with a range of 180 to 880 nanometers, so small, and the slit width 25 microns. So you can see here a spectra obtained from the oxyhydrogen plasma alone, and we can see only the OH radicals pick 307 and 309 nanometers. All the rest is black. We can see a small peak here, which is sodium doublet, but it's very, very weak. And my understanding with the Kevin's work could be eventually potassium that is in the water, the KOH, which is used as the electrolyte. So maybe. So I didn't analyze the output gas with the gas chromatography on top. So we can see the possibility here from the sodium lines can appear maybe with the combination of the potassium and oxygen. Once the plasma was applied on the graphite rod, I see a radical change in a matter of seconds. The strong sodium line appeared, also a potassium doublet here. And you can see here the oxyhydrogen radicals, OH radicals, just disappeared. And also you can see a really broad band around the 680 nanometers of peak. So in order to see if this is really sodium line, sodium doublet, I use my high resolution spectrometer. I can adjust the range and the center of the measurement. So it has a 4 nanometer range. So I can really confirm the sodium doublet here at the 589 and 589.6 nanometers. So it is really sodium. I used the software from one of the guys from internet, Tom Field, from our spec Astro. I can use this program with the optical spectrometer with the camera. So in these two spectra compared, I didn't saw any atomic hydrogen, neither before, neither after the applying of graphite. So the disappearance of the hydroxy radicals from the spectra and appearance of the strong peaks of sodium and potassium, as well as the appearance of this broadband here, pushed me to think that maybe the OH radical participating in creation of these sodium and potassium lines. All the oxygen and hydrogen just recombine with carbon in order to form elements like sodium and potassium. We can see that after. What is interesting in these graphics that there is no other peaks of specific elements that are present in the spectra. So I found in the work of Dr. Kevran, that was from his book Low Energy Transmutation from 1964. He showed that the following steps of the creation of the elements. So think is that, for example, magnesium or calcium didn't appear in the graphite on the spectra, but all the elements could be found later in the result of the oxyhydrogen treatment on the graphite. So this is just the setup to extract all these samples from the graphite. We have a macroscope here, microscope, standard microscope. I have a small device I made up here for the micromanipulation of these samples, and camera with computer. So these are interesting things. After the oxyhydrogen plasma treatment, the graphite surface was scratched in order to obtain this powder, which was analyzed under with two systems. The panel from the Schaeffetech, Switzerland, and the other one, older system, TESCAM, from the University of Lausanne in Switzerland also. So you can see here the optical picture, picture with the optical microscope, and on the upper side you can see the SEM. All these spheres are between 10 and 150 microns dimension, and there are a lot. I could count 100 spheres for square micrometer, so there is a lot of quantity. The main components of these spheres were carbon, oxygen, aluminium, but also very high percentage of the calcium, iron, and maybe a lower percentage of magnesium, sodium, and potassium. The graphite was analyzed before treatment. You can see here the result of the screening first, and then the precise measurement of different elements that I have found in these spheres. So I didn't ask to make all the precision measurements of all these elements. We have in the graphite rod, you can see that 99.8% about is carbon, and only 0.2% is all this. So you can see, for example, the component that is mostly in the graphite was iron, 0.12%. After the EDX measurement with the both systems, I made the calculations of these elements to see the percentage of the elements in these spheres, and they are mostly all same composition. The thing is that after the calculation, we have something like between 20 and 1800 times more elements in spheres than that was in the beginning. So if you take in account number of the spheres per square micrometer, so you can see that the amount of created new elements is really huge. Other things that are interesting is the elements that were found in these components, and those elements like chlorine and sulfur were found, but the problem is they weren't there in the beginning. So one of the possibilities is that for sulfur is the combination of two oxygen, and again the chlorine is made with sulfur and one hydrogen. So there is a possibility of this reaction to give these elements new elements. For the clever understanding, the impurities in the graphite rod before the treatment is important, as those are considered to be a seed for the creation of the same elements. Pure carbon rod, free from any impurity, can be or could give a poor result or maybe even no result. And to have some results with a pure carbon, you have to put more energy in the process. So as for the creation of synthetic diamonds, it's shown that certain proceedings need a seed for diamonds to be created, like in the CVDs or LPHT, low pressure, high temperature growth. So I think the same process is done in this experiment. One of the other elements that were found in the graphite powder was analyzed under the Raman with the Raman spectrometry in order to determine what the crystal structure is. So we can see here some sort of glass, and in fact it was a glass. It's an OFACT glass. In red you can see the composition of these elements, and the other ones are just for the comparison of the anode crystal and the anode glass, and so you can see that they're pretty straight, pretty confirmed the analysis. Here's another funny thing. A great number of these elements, like these ones, were found in the powder. And these elements are composed, guess what, 100% carbon. So, and you see the external structure represents some facets here. The extreme right image, you can see some multi-layer sheets composition inside of this, some sort of sphere, graphite sphere, carbon sphere, sorry. And I think this is an early stage of this one. So it's a growing process. Sergei Taskayev analyzed from some crystals formed by the meteorite dust fell on the Earth on February 15, 2013 in the area of Chelyabinsk in Russia. And the external structure of his findings resemble really good with this one. As you can see, these facets also, and the same composition is 100% graphite. He explained and present this structure as a crystal or polycrystalline variety of a cubic diamond with different colors going from black to dark green. The detection of the eventual strong beta and gamma radiation was performed with this 360-degree radiation detector, and it took me a time to do it, especially to weld all these small components here. So this module has, this detector has 12 modules. All modules have 6 detectors inside. 6 detectors per plate, and every detector has 3 diodes. These are silicon photodiodes. So the surface covered with these, all the complete surface was like 270 square millimeters. The noise, background noise was something like 30 millivolts, well under the background from the environment radioactivity, so even there is something, you could normally take a measurement of the radiation, but unfortunately I didn't find any radiation in this process, so I can sell it for someone who wants it. This is the last picture. I didn't know if I wanted to put it on the slide, but someone was give me asked me to put it, so I put it. You can see here the oxyhydrogen plasma going through a wall of the graphite crucible. From your place, it's like a normal flame, but if you take a look a little bit inside, it's there is a strange things happen. You can see these straight line inside of the plane that appears, and it's going from the entrance, I mean, it's not the entrance, it's the side, but the output, almost through the entire length of the plane. So, of course, there sure has to be done a lot of more research to see what is it, but it sure is a really interesting thing going on. I want to show you a small video about the oxyhydrogen plasma applied on the graphite rod. So the video is filmed with a small webcam, 30 images per second, and with a filter just in between to see what's going on. So I hope it's going. What can I call it? Say, one moment, please. One moment, please. I don't know. I'll give it time. So you can see the small parts going off of the carbon, and I just put a little bit more in under the plane. And what is interesting, as we discussed this morning, there are some points that appears here that stays bright for, in this case, it's a minute, but if you look at for normal timelines for 10 seconds, and they're just jumping from one place to another, but it's still very, very bright. So interesting, also interesting thing. You can see also small particles that are falling from this. A lot of people saying that is normal, sublimation process going with the oxyhydrogen plasma on the graphite. So maybe it is, maybe don't. I'm not sure about that. I didn't measure the CO2 above the graphite rod, but there was not enough fume to say that was a sublimation. So, contrary to the experiment from other persons like Sundaresan, Bockers, Ranford, Monti, Oshawa, and others, I didn't use electricity to make this experiment. It was oxyhydrogen plasma. And one of the few theories that I will discuss with a few persons, one of the theories which corresponds to this is the theory of Chris Ekman, which says that the electrons are trapped inside of the so-called Rydberg cluster in the linear water molecule, and release all these electrons in contact with the surface of the graphite rod. So the electrons penetrate inside the crystalline structure and break it apart, and that liberated the energy needed for the sintering, I would say, of these elements to produce other elements. You can see here the representation of new atoms by Kevin. So the next step is the research path of the nuclear transmutation. The oxyhydrogen plasma would be the following. First of all is the measurement of the electromagnetic field and electric current generated in the plasma. Eventually measuring the slow neutron radiation, if there is, and testing other materials and performing SEM, EDX, and Raman analysis. And Mr. McCuber said yesterday or before, we need the precise protocols to replicate this experiment. So I have a precise protocol here. So you get a good oxyhydrogen generator, take a graphite rod, put the graphite under the plasma, pick up the result, and enjoy the result. So that's it. So please consider the possibility of ways of getting LNR effects. Thank you. Yes.
What's that? Okay, I asked the first question. All these reactions should produce a huge amount of energy. Did you have any chance to make a correlative measurement at least?
Well, I didn't measure energy. I didn't have any calorimeter in place, or I wanted to do measurements with the optical, emissions like photons, but my spectrum wasn't calibrated, so I didn't make any measurement, energy management.
Okay, next step.
Okay, maybe I lost something, but did you cross-check the result of elements by ICP mass? ICP mass?
Yeah, I would.
Okay,
These, the result, for example, here, on the left, these are made by the analysis of University of Lausanne. They did all the measurement before,
yes.
and after was also double-checked with the EDX measurement. I didn't do the mass spectrum, yes.
ICP mass?
All these spectrum, all these lists
Yes.
did twice. So I'm pretty sure that the results are correct. Yeah.
Okay, thank you.
I have many questions for you, but the main questions: what the type of the power supply used in your experiment? What microwave?
This is the standard electrolyzer, water electrolyzer using
What plasma? What the generator is?
oxyhydrogen gas only. No plasma, no energy input, nothing about the plasma generated by the gas itself. I start.
Okay. And the second very strange results in your optical spectrum, connected with your optical spectrum, because of no
lines.
swan lines from graphite. Where is swan lines?
From the graphite.
C2.
Yeah. Correct. I will just come back to the, or for example here.
No. Oxygen OHIC, but there are no C2.
I didn't saw any C2 or C on the other.
It's very strange.
It is. The only thing what it's even stranger than that is the broadband, what you see here. And as I discussed with someone, it may be even stranger that that would not see the carbon lines inside. This broadband signifies something really strange is happening here.
And interaction between the graphite and OH jet will be in open atmosphere or not?
Open atmosphere, yeah.
Whereas CN, it's very strange.
It is very strange. The thing is that if you have only here, this one, this is OH radical, and that's for sure. And other lines are not present, so if there is a connection between oxyhydrogen plasma with acid, natrium from air, should be lines, but there isn't. This is picked up just at the output of the nozzle, of the on the nozzle. So you can see only these gas coming out, and there is no interaction with the environment.
Okay, I sure we can discuss.
Okay,
My
no problem.
last question after
Okay.
your presentation.
What is the temperature of this oxyhydrogen plasma?
Can you repeat the
What is
question?
the temperature?
I presented in Japan 3 years ago. I made a measurement of the oxyhydrogen plasma, but with a non-intrusive technique called the Moire deflectometry, which used two plates with in this case was 200 lines plates with laser flame, and that can give you a refractive index of the flame. And with that, with all the process, we can calculate the electron density of the plasma, which gives you the temperature. And the temperature was something like between 120 to 150 degrees C. Very cold.
150.
120-150. Very
My
cold.
question related, and I don't want to challenge you.
Yeah, no problem. No, it's okay.
Those sphericals that you produce, is it possible you melting out that material and you have, higher concentration in that melting? And before that, it was below the detection limit, if equally distributed in the graphite.
Well, we'll give you the table here. Come on. These, all these elements before are detected, and the smaller quantities, like in measurement, it's 0.0006%. I asked the university if there is a possibility there is other elements. They said maybe, sure, but the EDS mass spectrometer couldn't detect them because the quantity is too low. The thing is that we measure the percentage of these elements in the before and after, and percentage can be applied, in all different dimensional spheres, and you can see that there is a huge difference in percentage. So you cannot, even there is a talk about concentration of these elements in one place. There is no quantities, that much quantity of these elements, and not all these elements, just few of them, the 7 or 8 elements are connected into one sphere, and those spheres are like 1,000 spheres in a milligram. So the quantity is really, really huge after.
We'll have to cut it off there and move on to the next speaker.